So guys, on that happy note, this is where the rubber hits the road. Day one, we did rate expressions. As Josh just reminded us, you're gonna get them confused. Don't. They're not the same as rate laws. Then guys, last time in class, we talked about rate laws. We talked about the idea that a rate law is a mathematical expression that allows you to figure out what factors influence the rate of a reaction, including concentration, and then that K value that you need to know how to solve the units for. And as Josh again pointed out, that is related to the overall reaction order, and we figured out some stuff about that. Then guys, as we wrapped up Thursday's class last time, we talked about reaction mechanisms. And I gave you that ridiculous example of A plus B making C and D. And if nothing else, you got the idea that there could be a lot going on behind the scenes that is not represented in the balanced equation. Okay, we good to there? You're good? Okay, so guys, this is important. You need to have a really clear understanding of how you're going to be held accountable for this material. So, when you see the rate problem on the AP test, it's not a certainty. There will always be an equilibrium problem on the test. We'll talk more about that in chapters 16 and 17. So guys, we don't know for sure that there will be a rate problem, but it's one of the few things they are guaranteeing us will be on the test. I'm guessing now that we're looking at the new format of the test, there's always going to be a rate problem in free response. So when you get to that, here's what they're going to ask you to do. You ready? This is the summary, the culmination, the apex of everything we've been doing for the last few days. So guys, it's our goal for the day. Guys, what we're going to do today, and I don't think you need to write this down, you need to be able to verify reaction mechanisms. Those three words might be worth writing down. Verify reaction mechanisms. Guys, that's what they're going to do. They're going to ask you to write rate expressions. They're going to ask you to write rate laws. They're going to ask you to solve for K. They're going to ask you to take that value of K and plug in unique concentrations and come up with a new rate. They're going to ask you to do all this stuff. And then the very last thing they're going to ask you to do is verify a reaction mechanism. Now guys, let's think about what that means. First of all, what is a reaction mechanism? We talked about it briefly last time. What is a reaction mechanism? It's all the steps through which a reaction occurs. What do we call those individual steps? Elementary steps. What does elementary mean? Can't be simplified. Now guys, what about this? What does it mean to verify something? To make sure that it works. It doesn't mean propose. You will never be asked to propose a reaction mechanism. They won't say A and B make C and D, figure out how it happens. They will say A and B make C and D, this could be the mechanism, does it work? You see the difference? Okay, so guys, it's a two-step process. And I'm going to give you the steps right now, then we're going to build up to the way we do these two things, and then we're going to actually do one together. So guys, these are the two tests that this has got to pass. Test number one is this. Do the elementary steps add up, sum, to the overall reaction? We're going to call the overall reaction the subject reaction. So when you get to this question in homework, on the test, and on the AP test, and the question says, verify this reaction mechanism, you are then going to go two-step process. Step number one, do the elementary steps add up? Now guys, in order for us to understand that, we've got to talk about in greater detail, what are elementary steps? I know you already kind of know. What are they? What are the components of them? We need to do a little talking about elementary steps. Then guys, step number two. This is the second test to verify a mechanism, and it's this. Is the rate law Think about what a rate law is. Rate is equal to K times concentrations raised to reaction orders. Is the rate law for the rate determining elementary step the same as the rate law for the subject reaction? So obviously, in order to understand this, you've got to understand what a rate determining step is, and you've got to figure out how to write rate laws for elementary steps. So let me let you finish writing it down. We'll talk about some of the subtleties in that second test. Then, guys, we'll fill up your toolbox with all of the understandings that you need in order to carry out both these steps. And then we'll do one, and then we'll call it a day while you'll work on homework. You guys all caught up with me? You okay? Okay. So guys, this is the thing that's going to make this a little bit unique. So obviously, in order to carry out step number 2, you've got to understand what a rate determining step is. And it's easy to teach. You'll understand it. Go ahead. You'll understand it relatively quickly and we'll be fine. Guys, here's the thing that's tricky, and I want to introduce you to the trickiness right now. Guys, how do we write rate laws for reactions? What do we need in order to write rate laws for reactions? Balanced equations? Experimental data. Guys, you've got to keep that in mind. In order to write rate laws for subject reactions, you've got to have experimental data. Trial 1, trial 2, trial 3, where's your control? Where's the thing that's changing? How does that affect rate? But guys, here's the tricky bit. You ready? You are also going to write rate laws for elementary steps. And this is critical you understand this. You can write rate laws for elementary steps right from the balanced equation. You do not need experimental data to write rate laws for elementary steps. Any thoughts on why? Because they're elementary. Guys, think about this, and we're going to come back to it, but it's helpful to plant this seed right now. So, step back for a minute. Can we write rate laws for reactions from balanced equations? No, what do we need? Data. Why do we need data and not balanced equations? Why can't we write rate laws for reactions from balanced equations? What don't the balanced equations tell us? What's going on in the background, right? And because they don't tell us what's going on in the background, we've got to have data to write rate laws, because what we see in the balanced equation is nowhere near the whole picture, right? So what would then allow us to write rate laws for elementary steps right from the balanced equations? They're elementary. There's nothing going on in the background. That's the whole idea behind elementary. They can't be simplified. And because they can't be simplified, you can write the rate law right from the balanced equation because, as you pointed out, they're fundamental, they're elementary, and there's nothing hiding behind the scenes. We'll talk more about it in a minute, but I wanted to plant the seed with you now. So guys, again, the big idea is this. We're going to learn to verify mechanism. Two-step process. Step number 1, do they add up to the overall reaction? To really understand that, we're going to go back and revisit elementary steps. Then guys, number 2 is the tricky part. Does the rate law for the elementary step, which you now understand can be written from the balanced equation, does it match the rate law for the overall reaction, which can only be written from experimental data? Got it? Here we go. All right. So guys, some of this is going to be review. Some of this is going to be new. Let's talk about reaction mechanisms. So guys, you can write down what of this you want. I encouraged you not to write it down last time, but this is a revisiting. For some of you, maybe a first time, depending on how tuned in you were at the end of last class. This is what you need to know about elementary steps. So what are they? They are simple, one-step reaction processes that only depend on concentration. Now guys, why would they only depend on concentration? And the reason is because there's nothing going on in the background. So the more of something you have, the faster it will go. And that's always the case. So guys, the trick with these mechanisms, or with these elementary steps, is they will add up to give us what we call the mechanism for the reaction. So mechanisms are collections of elementary steps. Elementary steps are one-step processes that are strictly dependent upon concentration. There's nothing going on in the background. Now guys, again, the next thing that am I going too fast? Am I okay? So guys, the next thing that we talked about was the idea that we described these elementary steps based upon the number of particles. And we skipped over something. We touched on it, but not enough. We need to talk about it more. So as we describe these elementary steps based on the number of particles, as you may remember, the first one is what we call unimolecular, which means something either reorganizes or breaks apart. Then we've got bimolecular, which involves the collision of two different particles. And guys, I want to stop there for a minute because we need to make an important point. So tell me when you're caught up, and then we'll talk about the important point. You good? You with me? Okay. So guys, here's the idea. Reactions are described by mechanisms. Mechanisms are made up of elementary steps. Elementary steps are described by the number of particles that are involved in the step. Sorry. That's weird. The high school is calling me. Yeah, maybe. Maybe I got fired. Is it wrong to look for a new career? So guys, so the idea then is this. In a minute, you're going to start seeing, and I need you to think through this with me so you understand why. In a minute, we're going to start exposing you to mechanisms made of elementary steps. And here's the thing that you're going to find. Most of the elementary steps that you're going to see are going to be unimolecular or bimolecular steps. You will see a few termolecular steps, which is 3 things. You will never see tetramolecular steps. The question is why? And the answer is this. Guys, imagine that my hands are the reactants, and just watch. If this is a unimolecular step, there's only one reactant, right? And what is that reactant going to do? Either break apart or flip around. And that can happen all the time. The probability of something breaking apart or flipping over is really, really high. Now, guys, watch this. Bimolecular step. In order to have a bimolecular step, what has to happen to these two particles? They just have to collide, right? And that can happen really, really easily. So when you see mechanisms, you're going to see a bunch of unimolecular steps and a bunch of bimolecular steps. Why will you not see a lot of termolecular steps? Why not? Go ahead, Nate. Yeah, and you want to try it? This is actually kind of funny. Turn around, Jason. Okay, so in order for this to happen, right, as Nate said, all 3 things have got to hit at exactly the same time. So that means, hands up, no, yep, Jason and Nate and I have got to all hit hands at exactly the same time. How do we want to do this? 1, 2, 3? Wait, no. Okay. Is it 1, 2, go on 3, or 1, 2, 3, then go? 1, 2, 3. 1, 2, 3. 1, 2, 3. Oh, close. Okay, 1, 2, 3. Oh, ow. Okay. But you kind of get the idea, right? But was it possible, given we're a bunch of knuckleheads? We did okay, right? But now let's go tetramolecular. Come on, Eliza. Tetramolecular. 1, 2, 3, go. No, I got hit on the back. Okay, 1, 2, 3, go. Oh, 1, 2, 3. Oh, you get the idea, right? Okay, I know. All right. But guys, seriously, that's the idea. That unimolecular and bimolecular are very probable, because one thing can flip or break, or two things can collide, no big deal. But and we were trying, right? What was the first thing I did? How are we going to time this? Imagine if we didn't even time, I shouldn't have done that. Imagine if we just said, all right, let's make this happen. Even better yet, with our eyes closed. It ain't going to happen. And guys, tetramolecular is even less likely. So the idea then is this. Termolecular, yeah, maybe. But guys, termolecular steps tend to be very, very slow. Why would they be slow? Because they're not very probable. And guys, the bottom line is this. Tetramolecular steps in this class you will never see. And fundamentally, the idea is this. If you are a kinetic chemist, and you can actually make a living as a kinetic chemist, if you become a kinetic chemist, and if you're trying to figure out the mechanism for a reaction, and if your mechanism includes a tetramolecular step, many times if you were to try to publish that, they would ask you to revise it and see if you can come up with a mechanism that doesn't include that tetramolecular step, because they are so improbable that typically they just don't happen. Yeah.
So for
And that's the idea. If something requires a tetramolecular step, it's probably a couple bimolecular steps that you just haven't uncovered yet. But that's really what you do as a kinetic chemist a lot of times, is you're trying to figure out what those steps are. And when you see that tetra, maybe you're going, maybe it's a couple twos. Yeah, exactly. Yeah. So guys, again, anything beyond tetra probably isn't going to happen. Now, with that, I need to now introduce you to a new term that we're going to be using as we start looking at mechanisms. And guys, that term is the term intermediate. And maybe I should have underlined it to make it stand out, but you need to know this term. Guys, intermediates, when we look at mechanisms, you're going to run into things called intermediates. Guys, intermediates are substances that are formed by one elementary step and then consumed by coming elementary steps. Therefore, they don't appear in the balanced equation. They are not reactants, they are not products. They're also not catalysts. They don't show up in the balanced equation.
I guess they're like, a lot of the steps are fake intermediates.
You'll see them. I don't know if I would be looking for them frequently. Reactions certainly happen without them. But the more complicated a reaction is, certainly the more likely it is to create intermediates. I would go with that for sure. Mm-hmm. Absolutely, because they could be created in elementary step 1, then elementary step 2 could create something that then reacts with the absolutely. Yeah, yep, for sure. Not typically they are, but if they're not, it doesn't invalidate the concept. Okay, so guys, here's where we are. We understand that elementary steps are fundamental. We understand that elementary steps are described by their molecularity. We understand that uni and bimolecular, very common, termolecular, sort of tetra, don't even think about it. And now we understand there are these things called intermediates that are produced by one elementary step and then consumed, typically in the next step, but it could be subsequent steps, and that doesn't invalidate the idea. Yeah. Yes, but that's not the answer you're going to give. Bottom line is you'd never see that. But if you saw in a test a mechanism to verify, and it had a tetramolecular step, and your reasoning behind invalidating the mechanism was it's got a tetramolecular step and that can't happen, that would be wrong. The only way to invalidate or verify a mechanism are the two things we talked about before. Do they add up, and is the rate law of the rate determining step the same as the rate law for the overall reaction? So,
Right, so like if it were to be tetramolecular, would that just say right off the bat it's invalid and now we have to go through the math behind it?
no, well, and that's what Gavin was sort of getting at a little bit, and the answer is you won't be put in that position. I've never seen a tetramolecular step in homework or the AP test. You guys good to hear? Okay, so guys, this next slide is just a retelling of what we've already said. So let's do it really quickly. In order to write a rate law for a reaction, what do we need? Experimental data. In order to write a rate law for an elementary step, do we need experimental data? No. How do we write them? From the balanced equations. What allows us to do that? As Zach said, they're elementary. There ain't anything going on behind the scenes. But you guys would feel better if you got to write all that down, huh? Okay, so here we go. We cannot write rate laws for chemical reactions from balanced equations. Instead, we have to have reaction data. But we can write rate laws for elementary steps without experimental data. The way we do this is the coefficients for the balanced elementary steps are the exponents for the reaction orders in the rate law. And again, the reason that this works is because rate laws, as Zach said, are elementary, and the molecularity tells us their response to concentration change, because all it takes is collisions. The more stuff you have, the more collisions you'll get. I will now take a 5-minute break as you guys spend the time to write down all the stuff you already understand. See, guys, but this is why I explained it to you at first and then revisited it, because I think many times after hearing it the second time, you start to go, okay, that gels. I get it. Jay, do you have a phone with you? Does it have a countdown timer? Do you want to grab it? Or even just a stopwatch would be fine. Let's do a stopwatch. Don't be nervous. You guys done yet? Good heavens. How about now? You good? Okay. Are we good? Okay. So guys, we have one more thing that we need to talk about before we can get into this two-part process. Let's think about it. Part number one of the verification process is, do the elementary steps add up? You now understand what elementary steps are. You understand what it means to be elementary. You understand their molecularities, and you understand what intermediates are, at least on the surface. So you're all ready to go with test number one. Now, test number two is, does the rate law for the elementary step equal the rate law for the overall reaction? Now, so you understand how to write rate laws. You know the rate law for the subject reaction needs experimental data. The rate law for the elementary steps can be written from balanced equations. Now the only thing you got to do is understand rate determining step, and we're ready to go. So let's talk about rate determining step. So guys, what is the rate determining step? And it goes like this. If you have a reaction that occurs in multiple steps, so it has a multiple elementary step mechanism, the reaction cannot go any faster than the slowest step. And we call this slowest step the rate determining step. So then, functionally, by definition, the rate determining step is the reaction step that limits the overall rate of the reaction. I'm going to show you. Whoa. Parker and Zach, you guys are a part of this too, by the way. It's not just Jay. A little. Okay. Spencer could be in danger. You're fine. Okay, you guys ready to actually understand what this is saying? Okay, so guys, the analogy goes like this. We've got a reaction where Zach turns into Zach, Knappenberger into Baird. But we're going from Knappenberger as a reactant to Baird as the product, okay? And so this process actually happens with a two-step mechanism. Step number one is Knappenberger turns into Parrish, and then Parrish turns into Baird. Get the idea? But the way that this happens is these two steps have different rates. And so it turns out that the step where Knappenberger turns into Parrish, that happens at twice the rate that Parrish turns into Baird. So here's what we're going to do. So what I need you to do, Jay, is when I say go, you're going to start your stopwatch. And you feeling fast? All right. Every 10 seconds, you're going to say to Parker, go. Okay? And Parker, when you hear go, you are going to throw a paper ball to Baird. Okay? But every 5 seconds, I'm going to be throwing one to you. So you've got to catch these every 5 seconds and throw them every 10 seconds. You know what? Could you be my guy and tell me to throw every 5? Yeah. Okay. So you get the idea? So guys, let's contextualize this before we laugh at Parker. What step is the rate determining step? The first or the second step of the mechanism? Second step, right? Okay, so you got your stopwatch ready? You're counting every 10. You ready to go? Every 5. Ready, go.
Go. Go. Go.
No, that wasn't a go. Come back. All right, restart. Let's go a little faster. He's doing good. Let's go 2 and 4 seconds. Come back. 2 and 4 seconds. Parker was doing better than I thought. Okay, every 2 and then every 4. Ready, go.
Go. Go. Go.
Jay?
Go.
Oh, gosh. Oh, gosh, sorry. Okay, I'm out of balls. But stop there. You understand what's happening, right? What does Parker have building up in his lap here? Whole pile of stuff. So fundamentally, these balls are only getting from me to Zach as fast as Parker's getting them to Zach. We've got a bottleneck here. We've got stuff that's just building up. Could be an intermediate, but we've got stuff that's just building up. And so fundamentally, it doesn't really matter how fast I'm throwing things to Parker because they just back up until they get down here, right? Now what if we switch this around? Now what if I throw them every 4 and Parker throws them every 2? What's going to happen? He's not going to have anything to throw. But the second stuff gets there, he will have missed a go, right? Which means he can throw as soon as he gets it. Let's go every 4 again. Okay, so every 4, and then Jay, you're every 2. And if you don't have something to throw on 2, you can throw as soon as you get it. Ready, go. Oh, sorry. I heard the wrong go. 4 seconds is forever. You get the idea? Guys, they're going down there immediately because now Parker's just waiting for stuff to come in. So fundamentally, it's really just like we're doing this every 4 seconds. Because the second it hits Parker, it's over there. It's pretty good, right? So guys, do you understand the idea that it doesn't matter where the rate determining step is? If the slow step is here, stuff builds up. If the slow step is here, the minute it gets there, it just passes right through. You understand the idea? So hopefully, Josh, that answered your question. Why can a reaction only go as fast as its rate determining step? Do you now see it with paper balls? You get the idea? Okay. So what this all means then, guys, is that if we've got an entire process, let's bring this full circle. So we talk about verifying mechanisms. Say that you didn't know what was going on in the background. Say that you didn't know that this Zach to Zach process was actually Zach to Parker, Parker to Zach. Guys, because that would really be the balanced equation. The balanced equation just says Knappenberger to Baird. But as you start to uncover that there's something going on behind the scenes, the bottom line is when you look at reactant to product, you are going to be able to see that this reaction has a rate that is the same as the rate as the slowest step. Does that make sense? So what that means then, if you know the rate that this happens, and if you know the rate of the slowest step, what will be true of the two? They'll be the same, and that's step 2 of the verification process. And then the only other thing you've got to do is make sure the mechanisms add up. So Knappenberger to Parrish and Parrish to Baird actually adds up to Knappenberger to Baird, and then you're good to go. So if they add up, and if the rate laws match, you know you found a valid mechanism. Not necessarily the only mechanism, but at least it's possible. You good? All right, so guys, let's try this and see what we got. So here we go. Here's what we're going to do. I would encourage you to take note. Don't write this down. But it goes like this. You'll see. So guys, it goes like this. We have a reaction between nitrogen dioxide, NO2, and carbon monoxide, CO. And well, as it says, as represented below, and you probably want to write this down. You do want the balanced equation. It is suggested, we should be looking to verify the suggestion. That's the whole point of this. It is suggested that this reaction happens through a 2-step mechanism. Verify that this mechanism is possible. It's valid. It doesn't mean it's right. It just means it's not wrong. Verify that this mechanism is possible. So guys, these are the steps. And then the question again will be, is this possible? And guys, you do want to write these down. Let's talk terminology. This is called our subject reaction. And then these are obviously the elementary steps in the mechanism. 2-step mechanism. And as soon as you're caught up, we're ready to verify this mechanism. Ready to go? Okay, what's test number 1? Do they add up? So guys, in order to do that, all you've got to do is this. Draw a line underneath this. And then bring down all of your reactants. So we have NO2 and NO2 and NO3 and CO, and then our products, we've got NO3, NO, NO2, and CO2. That is the best that my board has behaved in like 2 months. I know, it knows its life is on the line, right? It's like my dog a couple of years ago. Okay, so now guys, let's simplify. I see an NO2 over here, and I see an NO2 over here. Oh gosh, did I do that wrong? Oh no, I did it right. I was looking for the NO3. Now guys, here's something interesting. See this NO3 right here? Oh my gosh, there it is again. What do we call that? That's an intermediate. That is a substance which is produced by one elementary step and consumed by a subsequent elementary step. By definition, as an intermediate, it does not show up in the balanced equation. Now let's look at what we're left with. NO2, CO, NO, and CO2. Oh my gosh, it matches the subject reaction. What a coincidence. But guys, that is what this process looks like, also allowing you the opportunity to identify an intermediate. Now that you see the intermediate NO3, do you have a pretty clear sense of what intermediates are? Is that okay? Okay. So, have we passed test number 1? Yeah. So how would you communicate that? And guys, when you write about this on the test, you got to be careful because your reader doesn't know exactly the way that we've taught this. So you don't get to say it passes test 1. That's not a universal idea. What you do need to say is this reaction is valid because the elementary steps add up to the overall reaction. And we now need to do test 2. But we don't call them test 1 and test 2. You need to express that the elementary steps add up to the subject or the overall reaction. Okay, so are you satisfied not only with what test 1 looks like, but the fact we've passed it? Okay. Excuse me, I'm hiccuping. Okay, so now guys, we need to talk about test 2. If you remember, or you can reread it, test 2 says this. It says the rate law for the rate determining step is the same as the rate law for the overall reaction. When you do this, you will typically write the rate law for the overall reaction first. So guys, what do we need in order to write the rate law for the overall subject reaction? Data. So here comes data. Write the rate law. And guys, what I want you to do is not just write the rate law, but maybe for the first time, depending on what you did with the homework, write out how are you going to justify your rate law to the AP graders. Because it doesn't matter if you get it right. This is one of the questions on the AP test that will be worth 1 point. It's not going to be 1 point for the rate law and 1 point for the explanation. It's going to be 1 point for the rate law, and if you don't explain it right, you don't get the point. So guys, try it on for size and write an explanation. You guys all done? No, you're not. Sorry. I don't want to rush you because I want you to do this well. Can we talk about it? Okay, so this is the way that I would approach it. I'm looking for controls. And so I look at trials 1 and 2 and I see that we're controlling NO2 and we're doubling carbon monoxide, and what happens to the rate? Doesn't change. So maybe my first sentence would say something like this. Referencing trials 1 and 2, when NO2 is held constant and the concentration of CO is doubled, the rate does not change, indicating that this reaction is 0 order in CO. Good?
This is saying a 0 order reaction.
That's fine. Absolutely. But make sure that you're indicating that it's the CO and not the NO2. Then, oh, there it is. Then I would go on to say, referencing trials 1 and 3, where CO is held constant and the concentration of NO2 is doubled, the rate of the reaction goes up by a factor of 4, indicating that this reaction is second order in NO2. You buy that? Okay. And from those two observations, we can then say that the rate law for the overall reaction would be this. Can I get an amen?
Amen.
All right. You know what that means, of course. We agree. Yeah.
So if you were to write as your answer rate equals K, like that NO2 to the 2, and then if you were to write the CO like
To the 0, it wouldn't be wrong, but it would certainly catch the eye of the grader. But it wouldn't be wrong. It's just not the way we represent it. Yeah. Okay, we good there? All right, now guys, we're ready to bring this full circle. So here's what we've got. We now have our overall reaction written above, and we've got our two-step mechanism written below. And we have already verified that the elementary steps sum to the overall reaction. We also now know this, and forgive me, I'm going to leave off rate equals, just because I don't have space. But we know that the rate law now for the overall reaction is rate is equal to K times NO2 squared. It's second order in NO2. You good with that? Okay, now we need to write the rate laws for the elementary steps. So guys, let's do step number 2 first. You're going to find this easier. So the rate law for step 2 then would be this. Rate is equal to K times the concentration of NO3 and the concentration of CO. We can write it rate from the balanced equation, so this would be CO. So this would be first order in NO3 and first order in CO. Is that okay? Okay, now the reason I did this one first is because I want to bring up a point. Guys, what would the rate law for step 1 be? Rate is equal to K times NO times, or NO2 times NO2, which is NO2 squared. So rate is equal to K times NO2 squared. What if this was a 2? Then what would it be? NO2 cubed. Because the coefficients are the exponents in the rate law. But that is not the case here. Okay, we're almost there. So guys, here's what we've got. We've got the rate law for the overall reaction. I guess I can write this up here. Rate is equal to K times NO2 squared. We now have the rate laws from the elementary steps. We wrote those by taking the coefficients and making them the reaction orders. Now here's the last thing we need to know. Which one of these is the rate determining step? And this is how they will tell you. Next to one it will say slow, and next to the other it will say fast. So the slow step is understood to be the rate determining step, and they will tell you which one it is. So look at what we've got. Step 1 is our slow step, our rate determining step. So you look at the rate law for the rate determining step, you compare it to the experimentally determined rate law for the overall reaction. Oh my gosh, they're the same. And so what does that tell you? The mechanism is passed test number 2, and therefore this mechanism is at least valid or possible or probable. Doesn't mean it's right, we just know it's not wrong. So there you go. So guys, that's what that two-step process looks like. Yeah. So you would simply say the rate law for the rate determining step equals the rate law for the overall reaction. Yeah.
So on the second test, the slow one always needs to match.
Correct. Yep. Yep. Whether the slow one's the first one or the second one, they have to match.
Why is that?
Because of the ball thing we just did. That the reaction can only go as fast as the slowest step, in the same way that I can only get balls to Zach as fast as one of us gets them there, but those speeds are described by these rate laws. Yeah, because, and again, the best way I know to describe it is the fastest I can get balls to Zach is determined by the slowest step in the things that get balls to Zach. So whether that's me to Parker or Parker to Zach, whichever one of those is slowest, it's as if that's the thing that is establishing the rate for the entire process, because we can't go faster than whatever that step is. Please, yeah.
Think of it as hourglass.
Okay.
So like, once you turn it over, push, all the sand is right here, except you have that little tiny slant that's slowly letting sand.
Yeah, you know what would be really cool in my head? What if you had an hourglass with 2 constrictions? And if they weren't the same, that would be cool. And if they weren't the same size. Yeah. Yeah, that would be a really, really cool analogy, because if you let it go one way, fast and then slow, eventually that middle vessel would fill up. If you flipped it over and went slow and then fast, it would never gather in the middle, but in either case it couldn't go faster than the slow constriction. That's really cool, Spencer. Yeah, just a second, Vanessa, go ahead.
So if you use a Parker is 4 seconds,
Yes.
if that Parker to Zach is 2 seconds,
Uh-huh.
is Parker to Zach a 0 order reaction?
That's a really good question, Everett, and it depends on the particular process. Not necessarily. Oh, wait a second. In the overall reaction, would that be 0 order? Is that what would whatever this thing is going there be in a 0 order reactant? Unless it's an intermediate, yes. Yeah. Yeah, absolutely. Go ahead, Vanessa. Are you sure? Okay, if it comes back to you, let us know. So guys, other things you want to explore? Okay, then here's your homework, but let me just, well, you'll see. Guys, this is a weakness with our book. They do not do a great job of offering you problems that allow you to practice at what we just did. Consequently, out of your Princeton book, on page 210, We are also, well, take a look at questions 1 and 2. They are also good examples of what these might look like.